Good morning. Thank you for the opportunity to come to present this audience. I bring a somewhat different background, come from epilepsy, and historically, I should disclose that I have never really delicately handled DNA or CRISPR'd them or Cas'd them. My early experience was mostly smashing them to pieces and doing tunnel labeling to see apoptosis. But much of what I'm going to present today is not what we do in the laboratory, which sometimes borders on autism, but trying to understand for this particular entity, because we have an interest in the interplay between autism and epileptic disorders. And in some cases of autism, even including this DNA locus, as you know, with Angelman, for instance, the epilepsy is not especially challenging. You go to other loci like Fragile X, the cognitive disturbance is more impressive. The epileptic phenotype is more like a benign Rolandic type of epilepsy. So while there is a relationship, they don't always go together. Then in the world of epilepsy, we also describe some syndromes as epileptic encephalopathies. What makes something an epileptic encephalopathy is you have an underlying disorder, you have issues, and you have seizures, but the seizures are bad enough that they are further contributing to a decline in your neurodevelopmental potential over and beyond the initial cause. And looking at the Dup15q patients, that we see a number of them, because of our relationship with Shefali now in particular, what I find is it frequently meets the criteria of that, because in many of them, the seizures are extremely difficult to manage, 40-50% of them presenting with infantile spasms, which, regardless of etiology, if you present with spasms, we do consider that an epileptic encephalopathy. So it produces a very interesting challenge as well. So what I hope to do here is to explore a little bit, again, going to this basic thing that we saw over and over yesterday. A lot of attention has been paid to the ubiquitin ligase-related gene or the Gaba receptor gene. And, coming from the world of epilepsy rather than proteosomes and neurodegeneration, I'm much more in the world of Gaba receptors. So one of the things I'm going to try to scan for you is the unanswered questions remain in different types of these syndromes. Is there actually a overexpression or underexpression? Again, does having extra copies of gene, does it actually give you more protein product? Are there actually more receptors? Is the action enhanced? And that's not always clear to me so far. But I'm going to focus on it and also try to look at what are these particular 3 GABA genes that seem to be very much in that area. That is the ones that code for beta-3 subunit, the alpha-5 subunit, and the gamma-3, and try to pull together what we know about them in this context, okay? So this is the basics of the GABA receptor. You see the presynaptic terminal with the GABA vesicles, and postsynaptically, you can see here that the receptor is a pentamer with the alpha, beta, gamma receptors, subunits, and here is a table that shows you a repertoire. So genetically, the alpha could be, for instance, 1 through 6, beta can be 1, 2, or 3, gamma can be 1, 2, or 3, and those are really the main important ones. The delta has interesting potential, but at least in this gene locus, we're not involved with that. Now, I just put on the top again to remind us that we're really interested in those 3. So to give you another note, this is a juxtaposition of the GABA receptor showing both synaptic and extrasynaptic variety. So one of the big differences is in the synaptic side, the alpha receptor subunits are usually 1 or 2, and you'll notice on the extrasynaptic side, it is 4, 6, turns out actually 5 often is in the extrasynaptic site. Those generally are sensitive to neurosteroids. The lack of gamma subunit makes them not substrates for benzodiazepines. The other important difference, the synaptic ones are important for signaling, so they have a very different time constant. So you need, they're generally low sensitive receptors, meaning you need a high concentration of the agonist, such as occurs during a quantal release, to trigger, but then they fade very quickly so you can signal again, ontogenically speaking. On the other hand, the extrasynaptic ones kind of set a baseline inhibition, so they are actually very, very sensitive to subtle changes in the concentration of GABA, and their action is very sustained. So they kind of set the level of inhibition rather than signal per se. And you need the gamma subunit for benzo, and here you have delta rather than gamma, okay? And I just magnified it so you can sort of see the details I'm talking about on the synaptic. So because of the way I described the time constant and the sensitivity, we call the synaptic ones to provide phasic inhibition, and the extrasynaptic ones to produce tonic inhibition. And they may have some interesting consequences, and that may become important for our alpha 5, okay? So here is again, just to show you that the most common variety that occurs all over the place is really the combination of alpha 1 with beta 2 and a gamma 2. And you can see the stoichiometry. There are 2 binding sites for GABA. It occurs in the cleft between the alpha 1 and beta 2, whereas benzo requires that gamma. That's why the extrasynaptic ones don't entertain or host benzodiazepines. The other important thing is to recognize that in many, many immunohistochemistry studies historically, as you know, our item of interest is the beta 3. This postsynaptic receptor, you don't have to worry about alpha 5 because that occurs in the extrasynaptic thing. But over here, historically, we used to think beta 2 and beta 3 are almost interchangeable. There's a lot of homology. One of the confusing things when you try to look at classic immunocytochemical localization is the antibody actually doesn't tell apart beta 2, beta 3. So in many of the early publications on GABA, particularly some of you may know this model of GABA receptor came from Richard Olson in the Department of Pharmacology here, okay? So now let me start with the alpha 5 because that's one of the things involved in this locus, right? So this is one of the early papers, and the only point of showing this to you is that the alpha 5 signal is quite weak in the neocortex, right? It does not enjoy as wide a distribution. And as I indicated to you earlier, note again in the bottom left, beta 2, beta 3, they don't even try to resolve it. Nobody thought of them to be historically very significant, right? On the alpha side, you can see alpha 1 versus 2, and I mentioned to you, alpha 1 is very common, but alpha 5 has a very low signal. However, in this image, this is actually rodent, you can see with in situ hybridization that the message is heavy in the hippocampus. For those of you who are not used to looking at it, if I can find the light. That's it, yeah. So that's the hippocampus, dentate gyrus, Ammon's horn. And you see here the beta 3 signal is also quite heavy there. And you also see it in the entorhinal areas. These are important structures in epilepsy, okay? So one of the very fun things to know is could an overdose of alpha 5, if that's what's happening, when you have a duplication, triplication of this gene dose, very interesting findings. The alpha 5 is one of those entities that actually we don't want to activate too much. And this could be one of the side effects of benzodiazepines that don't discriminate different subunits, okay? Because when they did a mouse model with alpha 5 knocked out, and you will remember it was mainly in the Ammon's horn and the dentate, not all over the cortex. Very specifically, they found that these actually improved their performance in the water maze. Okay? So if your patient feels a little goofy when they take clonazepam, we're probably activating alpha 5, and we would rather not. Okay? And what is also interesting is it really doesn't seem to be so much an epilepsy-related one, because if you look at even the homozygous knockout, they're really smart on the water maze, but they don't have spontaneous seizures, right? So the corollary is, if we're going to be dealing with epilepsy, we don't need to be activating it, but if you do activate it, it may have cognitive consequences. So we have a little human evidence for that too. So this is actually from a department of anesthesia that kind of, again, remarked that sustained increase, specifically in the alpha 5, seems to impair memory. Okay? This is very similar to the knockout animal in the water maze. Further evidence that may be very relevant to our problem is there has been an association with the alpha 5 subunit, and note again, gain of function. Meaning, it's the knockout that is smart. Agonism gave you memory problems and learning problems. And here again, these are actually shown in a paper specifically relating to autism, showing that alpha 5 could be a candidate thing. So I think taken together, we have many lines that kind of converge, that too much activation of alpha 5 subunit is not a good thing. Okay, and as to, is that an opportunity in the future, right, for therapeutic targets? And so this is a paper that came in the European Journal of Pharmacology. I'll just kind of highlight the fact this is mostly a paper on synthesis of chemical, which I sometimes look at because I'm an old medicinal chemist. But the key thing I wanted to emphasize to you is these are putative alpha 5 receptors, and they had good blood-brain barrier permeability, but remember, these are inhibitors, kind of like the knockout. The idea was to, they're devoid of sedative effect, which I'll tell you later, it's mostly alpha 1, like zolpidem is a good example, right? So they are devoid of sedative or proconvulsive or motor side effects, but enhance performance in the object recognition test. Okay? So it's a slightly different mode of learning than the visual spatial one that the Morris water maze measures. But now you have support that different modes of learning seem to be enhanced if you block too much activation of alpha 5. And in the Dup15q, it's possible that indeed, if there's an overexpression, too much of that message and the protein, that could be part of the developmental thing. Okay? Now let's go to the beta 3. I indicated to you earlier, beta 3 is the other one in this locus that gets reproduced. We historically didn't see too much. Many early studies and localizations show beta 2, beta 3 with a common antibody, and we have not seen so much physiologic difference until, again, Richard Olson's lab with Tom DeLore, a former graduate student and postdoc, generated this knockout mouse that actually had abnormal EEG, and hang on, and you can see that those animals actually developed epileptiform discharges and abnormal EEG background, and they found that they could in fact control that very nicely with the ethosuximide in that particular model. They had also the motor problems, like they equated it to an approximation of Angelman syndrome mice. Subsequently, they also showed the ethosuximide response was the beta 3 deficient mice had enhanced thalamocortical excitability. That is the thalamocortical oscillator that not only sets generalized spike waves when you are awake in a burst mode, but during the resting state, it's important to connect it to the previous lecture because it's the same circuit that's involved in sleep spindle generation. So they're part of the pacemaker circuit and are important in the circadian system as well. So there is clearly a disruption that may connect to this, the sensitivity you heard earlier. Okay? And so we found that here, now we go to the gamma 3. Okay? That is also kind of interesting because we don't hear a lot about gamma 3. I searched far and wide because we talked about alpha 5 and the beta 3. The gamma 3, it turns out, has some overlap in function with gamma 2, but I was very intrigued when I ran across this because it wasn't so much about routine signaling, but it really had a lot more to do with the tangential migration of neurons coming from the median ganglionic eminence. This is also profoundly important for the problem we deal with, and I would love to see if some investigators who have mouse models have looked at ultrastructural studies to look at interneurons, because this migration that occurs gives rise to, when there is interruption, what we call interneuronopathies. This is what we call tangential migration rather than the regular migration or the radial one. So we know very well that this process going from the medial eminence to this supplies most of the interneurons for the cortex. And one disorder we know that in fact does provide an epileptic encephalopathy with severe mental compromise and bad epilepsy, including spasms, is the Arx mutation. And in the Arx situation, you can see it's got mental retardation, epilepsy. There are many, many stories, including autism and epilepsy. So again, if there is a disruption in the gamma 3, it may be at a very, very early stage of brain development rather than day-to-day signaling. But it would be interesting to know. And so here is another one, again, looking at the clustering of the gamma aminobutyric. So what this pertains to is they showed that the gamma 3 is important in the assembly of different subunits to make the receptor. Could it contribute, in addition to the early development, also to a potential vulnerability to seizures? Well, one thing we do know is we know a lot about gamma 2, which I told you is very, very similar. But gamma 2 is in the mature system and is very commonly identified as one of the mutations in GEFS plus, febrile seizure syndrome. Okay? And in that, what we know, this is from Bob McDonald's lab in Vanderbilt, and you can see that the disruption in the gamma 2 structure makes it difficult to do the assembly. So the receptor proteins get stuck in the endoplasmic reticulum or the Golgi, and you don't end up with it. And you can see here from 3 minutes to 40 minutes, great disruption in the mutant compared to the wild type. So that has some relevance to the epilepsy. And I went to see this paper as a summary of what has been published about the epileptic phenotype. And so even though there's been some exposure to classic sodium channel medicines like carbamazepine, you would think that with the predominance of spasms and Lennox-Gastaut, that's probably would not be my primary choice. One of the interesting things, again, is the spasms reminds me whether the gamma 3 has something to do, like the Arx. The benzodiazepine thing is a funny situation because everybody in the 15q community always tells me, and to me it sometimes seems like a preconceived notion. They kind of avoid benzos, and I'm occasionally trying to talk them into it and try to explain that one benzo is not the same. One of the interesting things, even though it's a very small n, of the 4 patients, 50% actually reported better than 90% seizure reduction with clobazam. What is clobazam and what's different? This is diazepam, it's a 1,4 benzodiazepine. So is clonazepam and lorazepam, but this is 1,5. So it interacts with the receptor a little differently. So if you look at different subunit sensitivities, I give you an example the blue bars are zolpidem. That's mainly for sleep. And you can see it's overwhelmingly alpha 1 over 2, 3, or 5. Okay, the low 5 is good, which is why I personally like it better than Benadryl in the morning. You're clearer. Remember what I said about alpha 5? You don't want to activate it, right? So on the other hand, if you look at clonazepam, you notice it's quite non-selective. You get sleepy, you get stupid, right? But when you go to clobazam and its active metabolite that Sean referred to, N-desmethylclobazam or norclobazam, they do show selectivity to alpha 2. See, there, it's quite a bit less sedating. It's somewhat less on alpha 5. So, to us, you should not just speak of it as any benzo. And what I read in the Conant epilepsy article, that summary, is it just sweepingly said benzodiazepine just make you very sleepy. I have news for you. If you come outside the 15q community, clonazepam and Ativan make regular people very sleepy also. So I think that there's this preconceived thing that we shouldn't do them because, oh, we already have this issue. These things make you very sleepy. I don't know of anybody who clonazepam doesn't feel sleepy and goofy.
But that's not the reason, right, that we're worried about it. We're actually worried about it because of the sudden deaths.
Mm-hmm.
It's part of the professional advisory.
But I'm not finding good data to support that.
That's probably true.
Because the number of patients are very low, and then the SUDEP data would show that if you're having 90% seizure reduction, better than many other drugs, that's actually very good. Okay, so I'm close to the end. Finally, as I said, there's still a little confusion whether you get more or less protein in different modes of thing. There are obviously differences between the interstitial ones and the isodicentric ones. But as I told you, I'm not a good DNA jockey, and I sort of get a sense that you can't predict these. You really have to look for how they behave. And, whoops. Why is this? Oh. So the very last section is a follow-up. It was very interesting. I found this paper from Takumi, which we heard about yesterday in great detail. I just have one quick slide. But it kind of got my attention because all our AEDs typically are looking at sodium channels, calcium channels, various Gaba modalities. We don't actively use very much to do with the serotonergic system. But I liked it for a very interesting reason yesterday, because Professor Takumi's paper talked about a deficit in the low serotonin, and it also suggested that restoration early may have potential for improved development. That kind of intrigued me because I have also looked at serotonin from a seizure point of view, even though we don't have commonly very many drugs. I was kind of interested to see whether, he mentioned yesterday, I think fluoxetine, but there may be better candidates that may mitigate against maybe both seizures and development, possibly, again, it's a, wishful thinking. But nevertheless, I thought I would show you a piece of a very long table showing that there is a connection, and every time there is a downregulation of serotonergic tone, you get increased audiogenic seizures, spontaneous death from seizures, right, like SUDEP. On the other hand, if you see, again, activation elevates the seizure threshold, decreases spike wave discharges, increases survival, right? There seems to be some value here that we have not been doing too much. However, one of the excitements in the Dravet world is a serotonergic drug. It has been sort of modeled in zebrafish with a number of analogs, that fenfluramine is an old classic drug. Most people in America know it as part of the fen-phen duo that cause cardiac issues. So there's some caution. However, the idea for epilepsy is not in such a combination and in a smaller dose. And more importantly, fenfluramine is not very new. I digging back, I found that the first person to use fenfluramine was Henri Gastaut. I think many of you know about Lennox-Gastaut syndrome. So Henri Gastaut in Marseille actually used it in some photosensitive epilepsies that are very refractory. And more recently, this is a paper from the trial by Zogenix. Professor Livon Leger from Leuven University in Belgium has been very involved with this. And you can see the seizure count. This is, pretty impressive, sustained over a year in Dravet patients. So this is a study with, it's the blinded, controlled, randomized, low dose, high dose versus placebo. So, based on that, very recently, the company was awarded a patent for that. So my very last slide really is going back to yesterday's model. Is this something we may want to try? Because we have these youngsters with very early bad seizures. We haven't really done great with anything so far. And I think you heard Sean talk about CBD. I continue to be a little bit underwhelmed, by the real data. I think there's a lot more passion than very objective, because even in a unblinded open label, they came up with 35-40% seizure reduction. That's less than what FDA expects to approve something like Keppra or Trileptal, even in an open label. It probably has some very special applications, potentially, but for many things, I think there is a enchantment. I hear in the clinic it's natural, and they're disturbed when I tell them gluten is natural, and they're dead set against it. But anyway, I think this is something Sean and I have been talking about to see whether your community would be interested in looking at this. And the other thing is I would continue to watch with interest whether some sort of alpha-5 blockers may have a future. Right now we don't have anything commercially. Because those things kind of make sense to me. Not saying anything about the UBE. This is the world I know. So I'll stop there. I have not acknowledged all my lab people because this is not one of my research things. It's more a educational thing, trying to pull together things we think about and talk about in my world, but not our work. Okay. Thank you very much.